So you can see in section 1.3, we've got a little vocabulary we're going to go over. And this is going to talk about what happens when you see, oops, this symbol somewhere, okay? When you see that, what does that mean to you? Okay, we think of that, that's a square root when it looks like that. Have you ever seen it where sometimes they put a little number in that spot? Okay, so we're going to make sure we know what all these things are called. Basically, we're talking about roots. They don't all have to be square roots, but that's the one we're most familiar with. So what do you think belongs in this blank? The number or expression inside or underneath a radical sign is called the, what do you think these words up here, which one would it be? It's this one right here, radicand. So if we had something underneath that radical sign, that's called the radicand. Okay? Now, number 2 says a number with a rational square root is called a something. Now, if it's a rational square root, it means when I take my square root, what comes out is a rational number. So if I get the square root sign to go away, that means this was a what? Say again? Well, I took the square root, and when I take the square root sign goes away. Look at these words. What does that mean I had? A perfect square. Good job. Okay. So number 2 is perfect square. Now it's rational because it could be a fraction. And as long as the numerator and the denominator are perfect squares in a fraction, I can still take the square root of that and get rid of the square root sign. Now there's a little typo issue on number 3. And this is missing. So it should look like that, kind of like what we have up here. And the N is in the place where you see the 3 up here. Do you know what that number is called if it's up in the corner on a square root sign? It would be a cubed root if it's the number 3, but since we've got an N here, it could be any number. And that is called the index, okay? So in other words, when I don't see a number there, I automatically know that's really a 2. It's sort of like we don't have to put a 1 on something as an exponent because we understand that it's 2 to the first power if I don't see an exponent. I don't have to put a 2 there if I'm taking the square root because we understand when we see the sign, it automatically means square root. But if I want any other kind of root, I have to put that number there. And that number is called the index. It tells me what kind of root I want. Okay? Now, this is saying the number b is a something of a if, and this should be an exponent. So let me write it the way that it should look. If b squared equals a, then what would you say is true about b? It's a what of a? In other words, if I could square a number and it gives me a, it means this number would be a, let's look and see what's up here. How about a square root? Think about it for a minute. If I took the square root of each side, I'm going to change colors so you can see that. So if I took the square root of each side, oops, then what I have is the square root of b squared is just what? What does the square root do to a square? Cancels it out, basically. Think about it for a minute. If I asked you, what's the square root of 25, but then I'm going to square that, what does a square do to a square root? Cancels it out, because the square root means what can you multiply times itself. The square means now multiply it times itself. This is the same thing, kind of going in the reverse order. Square root is saying what could multiply times itself to give you this, but what's already being multiplied times itself is b. So this is saying that b would equal the square root of a. So that's why the number b is a square root of a, as long as b squared equals a. Okay? Don't get too stressed over the, think we're playing mind games here, that we're just trying to get some basic vocabulary understanding down. Now, again, we're missing this little symbol. Okay, so let's go back and just say, if I have that kind of symbol, something that looks like this, and it can be any number in the corner, might be no number there at all. That entire expression is called a what? Radical expression. Good. So radical expression goes in this blank. And do you know what the, there's another name for a positive square root of a number. What do you think the other thing is you could call it? Besides positive square root, it's the
Principal.
that is right. You know what the principal means in this? If something is principal, it means it's important or primary. So we are going to understand that when we see a square root sign, if I asked you what's the square root of 25, what would you tell me the answer is? It's 5. Now technically, is there more than one number I could square? And the answer would be 25. I know 5 times 5 is 25. Is there anything else I could multiply times itself and get 25?
Oh, 25.
How about negative 5? What's negative 5 times negative 5? Ah, there's actually a positive root and a negative root. But if there is not a minus sign in front of the square root, it's automatically asking you just for the positive. Okay, so if that square root sign's already there, it's asking you for the positive or the principal square root. But you need to realize there's really 2 roots, a positive and a negative. Okay, so far we all right? All right, a real number that is not rational is called a what? You see it? Irrational number. There you go. So a real number that is not rational. What does it mean if it's not rational? If it's rational, I can write it where it looks like a what? A fraction. So if I can't write it like a fraction, remember we talked about some different numbers that are irrational. What about something like the square root of 7? What if you put that in your calculator? What does it give you? Gives you a decimal, and the decimal doesn't end and it doesn't repeat. So that's why it's irrational. I can't make that into a fraction. There is no fraction that'll give me exactly the square root of 7. Okay, let's see what's left. I see 2 things that aren't circled. I've got radical and I've got cubed root. What do you think goes in the blank on 8?
Cube root.
A blank is a radical sign and the number or expression in it. A radical. So number 8 is radical, which means number 9 is going to be what? Yes, the number b is a cube root of a if b to the 3rd power equals a. So if I can multiply something times itself 3 times to get that, that tells me that this number I was multiplying is a cube root. Okay, so far so good? Then let's make sure we understand how to do some things with these roots. If it asks me to find all square roots of a number, and I just have a number and there's not a radical sign on it, how many roots would there be? Okay, that's all right. Let me say it one more time. If the question says find all square roots of each number, and I don't see a square root sign on top of any of these things, how many roots will there be?
More than one.
What do you think? Is it more than one or just one? Because how many roots are there? There's a positive and a negative. Very good. So if it's asking me to find the square root of 625, you guys have a calculator? You don't know it off the top of your head? What does your calculator tell you the square root of 625 is? It's 25, but that means not only is 25 a square root, negative 25. So if it tells me to list all of them, it means give both the positive and the negative. Now, how do you take the square root of a fraction? Yeah, you're going to take the square root of the top and the square root of the bottom. So you can think of this as the square root of 49 over the square root of 144. So I'm going to get the fraction 7 over 12, but we said because it's all square roots, I need positive and negative. A little shortcut for that is you can put this little plus or minus sign in front. And that's a shortcut way of saying we need both the positive and the negative. Okay, now let's see if you can figure out what it's going to be on 3. 121 over 196. So what goes in the top of the fraction? 11. What goes in the bottom of the fraction? If you do the square root of 196, you get 14. And then what should be in front of this? Plus or minus. Good job. Okay, that makes sense? Now, tell me what looks a little different on number 4, because that says find each square root.
They gave
The square root sign is there. And if the square root sign is there, how many answers will I have? Only one, and it'll be what sign? Good job. All right, so square root of 400 is positive 20. Now, see if you can do the square root of 900 over 49. We can separate it into the square root of the top over the square root of the bottom. That's perfectly legal. And that's going to give us what? 30 over 7. And again, it's just the positive because the square root sign was there. Okay, look at number 6. What's this going to be? So he says 50 over 80. Do y'all agree with that? The square root of 2,500 is 50. Square root of 6,400 is 80. Now, does that reduce down?
You said reduce it.
Mm-hmm. Anytime we get a fraction, we don't want to stop until it's in simplest form. So if that reduces down, we need to do it. That's, say it again, 5 over 8. Okay, give me a quick signal. Are we here, here, or here? All right, most everybody seems comfortable at this point. That's a good thing. So let me scroll to the next page and let's talk about what happens when it's not a square root anymore, but maybe it's a cubed root or a fourth root. Ooh, okay. Now, we're going to go back to something we talked about on the very first day, prime factorization. And I'll tell you why. You might have a button on your calculator that's a cubed root. Probably you don't have a button on your calculator that's a fourth root. Now, depending on your calculator, you may have a place where you could put in a number for the root, and that's fine. But I want you to understand how you can figure it out if you can't get it on your calculator or you don't know how to get it on your calculator. Now, number 7 wants me to figure out, can you tell me in words what that means, cube root of negative 64? What am I actually looking for? A number that what? Multiplies by itself 3 times, and the answer is negative 64. Now, anytime there's a negative under a radical, here's the first thing you're going to have to ask yourself. Is it possible to multiply some number together 3 times and the answer would end up negative? What's a negative times a negative times a negative? It's a negative, right? 3 negatives multiplied together would be a negative. So that tells me this works. What if that hadn't been a cube root and it had been a square root? Can I multiply something times itself and get a negative 64? Because a negative times a negative gives me a positive. There's no way that the same number multiplied together 2 times would give me a negative. So got to watch out for that. If it's an even index, if the root is 2 or 4 or 6 or whatever, you can't have a negative under there. It's going to mean it's not a real number, okay? But as long as it's an odd index, we can multiply something together an odd number of times and get a negative. Now, here's what this tells me. I know it's got to be a negative number. I'm just not sure which one. So here's how I would figure it out if I don't automatically know what number multiplied by itself 3 times gives me 64. I'm going to start with 64. How could prime factorization help me? If I need something that multiplies together 3 times, okay, then I'm going to have to see if I can get some number that shows up 3 times in my list. And then that would be a root, right? Let me show you what I mean, okay? So tell me on prime factorization, what's the smallest prime number that's going to go into 64 evenly? 2. 2 goes how many times?
32.
Yeah, still even. So go again. 2 goes into 32.
16.
All right, still even. 2 goes into 16.
8.
2 goes into 8.
4.
And 2 goes into 4.
2.
2 times. Now that's a whole bunch of 2's being multiplied together. And I was looking for something I could multiply together 3 times, but I have 1, 2, 3, 4, 5, 6 of these 2's. So here's what you do. My index is 3. I'm going to circle up 3 of a kind. And then I have another 3 of a kind. So think about it this way. If I was asking for the cubed root of some negative number that is 2 times 2 times 2 times 2 times 2 times 2, okay? It means if I've got something multiplied together 3 times, it can come outside the radical, right? That's why I've got that group of 2's, and then I'm going to have this group of 2's. So you're going to take 1 from each group you circled. It comes outside the radical. And that tells me the number 4 should be what I could multiply together 3 times to get 64. Now, how can I double check that? Yeah, go to your calculator. See if 4 times 4 times 4 is 64. Is it? Yes, it is. If you knew that, you don't have to do this. If you didn't know what the answer should be, this will help you find it. So the cubed root of negative 64 should be what number? Negative 4. Because if I multiply negative 4 times negative 4 times negative 4, I get negative 64. Does that make sense? Okay. Let's look at this next one. It's the 4th root of negative 625. All right. Now, what do you think we should do with that first? What?
You multiply 2 times 2?
Yes. Anything, whatever your index is, that's how many you're going to circle at a time. And then 1 from each group that's circled comes out and gets multiplied together. So that's why we got 4. 2 times 2 was 4. Now, do you remember what we looked at first on the one above? What do we try to figure out?
Square root of 64.
Well, when we looked up here, we said, okay, there's a negative number, and I got to figure out, can I multiply some number times itself 3 times and get a negative, right? Because I checked on the sign part first. What do you notice on 8? Okay, the index is even. So it's saying, is there a number you can multiply together how many times? 4 times, and the answer is what? Negative 625. Is that possible? No, because if I have an even number of negative signs multiplied together, my answer is what sign? It'll be positive. So what this is no real solution. It's not possible to multiply some real number together 4 times and get a negative number. Now, if it had been the 4th root of positive 625, do you think maybe we could have figured that one out? All right, what would you have done? The factorization. So if we try to do prime factorization, what would be the smallest prime number that goes into 625 evenly? It's not even, so it's not 2. Okay, Patrick is saying 5. Do you remember how to tell if 5 goes into a number evenly? What does it have to end in? A 5 or a 0. As long as it ends in a 5 or a 0, 5 will divide into it. Now, 5 will go into 6 one time with 1 left over. 5 will go into 12 2 times with 2 left over. And how many times will 5 go into 25? 5 times. Okay, so 5 times 125 gives me 625. That still ends in a 5, so I'm going to go again with a 5. 5 goes into 12 2 times with 2 left over. And 5 goes into 25 5 times. And again, you use your calculator to do the division. Okay, I'm getting kind of excited now because I think this is going to work. What goes into 25 that's prime? 5 goes 5 times. Now, remember, what are we looking for to simplify? I need how many of a kind? 4 of a kind. Do I have 4 of a kind? I sure do. I've got 4 5s that multiply together to give me 625. So if I asked you what's the 4th root of 625, what would you tell me is the answer? Positive 5. That's right. Make sense? Okay, so that's how we can simplify radicals, especially when we get something that's not a square root and we don't have any idea what you could multiply together that many times to get it. Now, sometimes we might have to multiply radicals together. They may give us some to multiply together. And I'm going to tell you, for what we're about to do, there's more than one way you can approach this, all right? So if you see something different and you say, would it be okay if we did it this way? Ask, because sometimes it's helpful. You may see something that somebody else will go, oh, I like that. That makes more sense to me, or that's easier. So here's what I do when I look at this. On number 1, product rule. Now, the product rule simply says, I'm going to multiply these guys together. And as long as the radical has the same index, in other words, these are both square roots, right? Then I can multiply the numbers together and put them under one radical. That's perfectly legal to do. So for example, if I had the square root of 2 times the square root of 3, that would equal the square root of 6. Make sense? Okay, so I can, if I have 2 separate radicals, as long as the index is the same, if they're being multiplied, I can put them together as 1. Now, before I do that, I'm going to check to see, is there anything that would be a common factor between those 2 numbers? I have 13 and I have 5. Those are actually both prime. So that tells me that there is nothing that could simplify as far as common factors with those numbers. So I just multiply 13 times 5, and it gives me what number? 65. That's the square root of 65, and that's as simple as it gets. Now, what do you think we could do on number 2? Okay, here's one way we could go. We could multiply it. So how much is 7 times 7? So this is asking for the square root of 49. Well, wait a minute. Do I know what the square root of 49 is? It's 7. Now, do you see a little shortcut we might have noticed? Isn't this the same thing as the square root of 7 squared? Because I'm multiplying it times itself. So it's saying, what number can you multiply times itself to get 7 times what number can you multiply times itself to get 7? I'm multiplying the same thing times itself. They're basically going to cancel out those square roots. If these are the same number, when you multiply them together, you've created a perfect square. It's just going to be the number that was under the radical in one of those. Does that make sense? You can do it this way, but if you will notice, that's really the square root of 7 being squared. That's a shortcut way to get there because the square would cancel out the square root. Okay? Now, look at this guy. I got square root of 10 times the square root of 30. Anything you notice about that? What do you want to do? Can we multiply together? Okay, so let me show you, here's two ways you could go. If I multiply them together, this is going to equal the square root of what number? 300. Now, you remember how we used prime factorization to simplify just a little bit ago? Let's try that with this guy. So if I start with 300, is that even? Yes. So 2 goes in there how many times? What's 150? Is that still even? Yes, 2 goes how many times?
75.
But that's not even. But what goes into 75?
3.
3 would go
25.
25 times, and then 5 goes 5 times. Now remember, this is a square root, so I'm looking for how many at a time being multiplied together. If it's a square root, I want 2 at a time, pairs. Do you have any pairs here?
2 and 5.
I got a pair of 2s, and I got a pair of 5s. Here's the way this works. I didn't get everything circled up. Whatever I've circled up gets to come out from under the radical. Basically, you get a jailbreak as long as you got a friend going with you. Anybody who has no friend gets left behind. So when we pull them out, whatever we get to pull out, we multiply together. So what's 2 times 5? 10. But that 3 has to stay underneath the square root. Now, if you've got your calculator, I want you to double check something for me. Put the square root of 300 in your calculator, and I think you're going to see an ugly looking with this. Double check it. Okay. Now, put 10 times the square root of 3 and see if it gives you the same ugly little decimal. Did it? Can you figure out how to do 10 times the square root of 3 in the calculator?
Yeah,
Gave you the same number. That lets you know you got it simplified correctly. These are simplified radicals. That's what we're working on here. Because we're going to need to know how to do that when we work with the quadratic equation formula. You guys remember that? Ah. Now, Patrick, I want to kind of go the direction you were thinking, because there is another way you could do this. You said something about a common factor. What did you notice? Well, how could you factor 30 to where, is it possible that you could use 10 as one of the factors? 30 is the same thing as 10 times what? 3. So here would be a different way you could get there. And if you like it, it's okay to use it. But the key is, I noticed there's a way to get 30 written as 10 times something. So the square root of 10 is still here. But 30 could be written, or the square root of 30 could be written as the square root of 10 times the square root of 3, couldn't it? So just like if we have 2 radicals being multiplied together, we could write it as 1. We can also factor and separate it into more radicals. How would this be helpful to get here if we went this way? What do we say happens if I get the square root of 10 times the square root of 10? It basically cancels out the radical, and wouldn't that equal 10 square roots of 3? Another way to get there, if your numbers have common factors, you might find that that works out. Make sense? All right. Your faces are a little hard to read at the moment. We'll see how this goes. Okay, so on number 4, we got square root of 13 times the square root of 8. Now, I know they don't have anything in common, and I can multiply them together if you want to do that. But I notice, is 13 a prime number? There's no way that, I mean, that guy's just still going to be there, because 13 isn't going to go into 8 evenly. And I'm going to have a square root of 13 for sure. But maybe the square root of 8, I could simplify a little bit. How can I do prime factorization on 8? 2 goes, and 2 goes 2 more times. Now remember, it's a square root, so I'm looking for how many at a time? 2 at a time, pairs. So if I circle up a pair of 2s, let's see if we could rewrite this guy as the square root of 13 times. Now what's going to come out from under the radical? Yeah, this pair that I circled up comes out, but this guy still has to stay behind, doesn't it? Okay, can you multiply the square root of 13, excuse me, times 2 times the square root of 2? Because that's really what I have here. What do I have that's outside the radical? 2. Underneath the radical, I've got a square root of 13 times the square root of 2. Now multiply those together. What's that going to be?
26.
And it's under the square root sign, right? 2 square roots of 26. That would be my simplified answer on this one. I could have multiplied 13 times 8 and done the prime factorization, but I still would have only gotten a pair of 2's to come out, and there would have been a 2 and a 13 left behind. So that's one way you can get there as well. Okay, let's see if this sort of makes sense. We're going to try to simplify these down here. Now, what do you think this means if I see a negative sign in front of the square root? It means I want the negative root. So that's going to tell me this is going to equal negative something. Okay? Can you figure out how to simplify the square root of 180? I'm going to give you a second to work on that, and we're going to see if you need. So let's talk about it for a second. When you did your prime factorization on 180, I'll do it over here. Most of you started with 2, because that's the easiest one. You cut it in half. That's 90, and 2 goes into 90, 45. And then it kind of depends on what you saw here, because you had a choice. What could you divide into 45 that's prime? Either 3 or 5. If you did 5 first, then it went 9 times, and you have a 3 and a 3. If you put a 3 here, you would have had another 3 and then a 5 at the bottom. Either way is fine. But when I look at how this factors, do you see pairs? You're supposed to say yes. Yes, okay, good. Pair of 2's, what else? And a pair of 3's. This is the part we got to remember, because a lot of times students get mixed up on which part goes outside the radical and which goes underneath. Remember, you got to have a friend for a jailbreak. So as long as I've circled up a pair, that's going to be what's coming out. And whatever I've circled, I'll take one out of each of those groups and they multiply together. So on the outside of the radical was what number? 6. The 2 times 3 gives us 6. The negative sign was already there. Now it's a negative 6. Under the radical, I have 5. Okay, give me a quick signal. How are you feeling about this now? All right, good. Let's see if you can do the square root of 405. What this should be. The square root of 405 is equal to what? What goes on the outside? 9 square root of 5. Now, if you weren't sure how we got there, then let me come over here to the side somewhere. Actually, I think I'll do it right up here. 405. I think almost everybody said, hey, I know 5 goes into that evenly. If you divide 5 into 405, it goes 81 times. Now, here's where you got to be careful. Several of you got off just because you used 9, but 9 is not prime. And remember, we're trying to use prime numbers. So if I add 8 plus 1, it equals 9. That tells me 3 divides into 81 evenly. It's not an even number, so I know 2 doesn't go. Didn't end in a 0 or a 5, so 5 doesn't go. But 3 does go, and 3 goes in there 27 times. And 3 will go into 27 how many times? 9 times. And 3 goes into 9 3 times. Because it's a square root, I was looking for pairs. And that's how we came up with 9 on the outside, square root of 5. Now, cube root of 1,000, that means I need some number multiplied times itself 3 times. The answer is 1,000. Do you know what it is? You might know what it is. If you didn't, you can still use the prime factorization. I will tell you that you're going to get 6 factors using prime factorization. You get 3 of one number and 3 of another number. It is a perfect cube, so you don't have anything left behind underneath the radical, okay? And what do you think it is? It is 10. 10 times 10 times 10 is 1,000. Some of these you can kind of play with in the calculator and see, but you can always do the prime factorization if you can't figure it out just by looking at it. Okay, this is very similar to what we did up above, except these numbers are a little bit bigger. So ideas on the square root of 11 times the square root of 33. What would you maybe want to try here? You think what? Go ahead and say it. So factor square root of 33 into, there you go. If we think of the square root of 33 as the square root of 11 times the square root of 3, then we can see we have a pair of square roots of 11. So how's that thing going to simplify? What's going to come out from under the radical? 11, because I had a pair of those. What's under the radical? Square root of 3. Good job. Okay, see if you can do square root of 20 times the square root of 10. Now I can multiply it together and do 20 times 10 is 200 and do my prime factorization on 200. Or if I see a way to factor 20, I might be able to get there a little faster. When you think you know what it is, let me see hands, just so I can tell how long it's taking. Got one. Got it? No? Okay. And you can multiply 20 times 10 and get 200 and do your prime factorization on 200. That's not a problem. That works every time. Now, since you said you already had it figured out, Patrick, I want you to tell me what you think the answer is. Okay, he says he thinks it's 10 times the square root of 2. Let's double check, because I'm going to multiply the 20 times 10, and are we all in agreement? This has got to be whatever square root of 200 is, right? So if I did the prime factorization on 200, what would you divide into 200 first? What prime number? 2 goes 100 times. Is that still even? So 2 goes 50, still even. 2 goes 25, but what goes into 25? 5 times 5. Okay, what am I circling up? 2 at a time, pairs. So here's a pair of 2s, and here's a pair of 5s. Does that make sense that it would be 10 on the square root of 2? Yes, you did it by factoring square root of 20, right? To get there faster? Is that what you did in your head, basically? Uh-huh. 10 times 2, right? And that would be the same thing we did over here. He rewrote the square root of 20 as the square root of 10 times the square root of 2. Doesn't matter which way you go, you're going to get the same answer. Okay, you just got to figure out what works for you. Now, number 10 looks a little sneaky to me, because I can't just factor 18 and get 24 times something, and I can't factor 24 into 18 times something. So what would I maybe need to think about doing? Say again? Okay, when you say reduce, tell me what you mean. All right, let me give you a suggestion. Do you think I could maybe figure out what the greatest common factor is between 18 and 24? What do you think is going to divide into both of those evenly? 6 would, right? Could I maybe factor these as 6 times what gives me 18? 3. So this is the same thing as the square root of 3 times the square root of 6, right? All right, tell me about the square root of 24. That's 24 is going to be 6 times what? All right, so I could think of this as the square root of 6 times the square root of 4. Agree? Now, what do you notice we've got a pair of? Square root of 6's. So if I were to circle those up, then I know that's equal to 6. I'm left with a square root of 3 and a square root of 4. But did you notice something about the square root of 4? It's a perfect square. It's 2. So this is 2. The only thing that's going to keep the radical is the square root of 3. If I clean that up, what is that going to equal? That's it, 12 times the square root of 3. Now, you probably won't see a lot of these, but if you do have radicals being multiplied together, that's how you could simplify them. Okay, so if it's asking for your answer in simplified radical form, it means if there's anything that can come outside the radical, then you need to bring it out. Okay, so we talked about multiplying. Now let's talk about dividing. We've already looked a little bit at it, and I think you guys can probably do something like number 11 already, because we said if we're taking the square root of a fraction, then is it possible to take the square root of the top over the square root of the bottom? And as long as these are perfect squares, that's what you want to do. It's all going to depend on the numbers in your fraction, which way you want to go. So if I separate these out and make it the square root of 25 over the square root of 81, what's the square root of 25? And what's the square root of 81? 9. And how can I double check myself just to be sure I've done this right? If I square 5 over 9, if I do 5 over 9 times 5 over 9, it ought to equal whatever's underneath the square root sign, right? Okay, so we're good on that. Now, the problem here is if I separate, are both of these perfect squares? Is one of them a perfect square? Which one? 121. So what would this equal if I clean it up the rest of the way? I still have square root of 13 on top over 11 on the bottom. And I'm done. That's all I can do. As long as I don't have a square root in the denominator on the fraction, I'm good. Okay, so that would be my answer here. Now, we've got some funny looking things on 13, 14, and 15. Our goal is to try to clean up, reduce down what we can, where we can. So what do you think maybe we should, what should we try to do on 13? So maybe if we simplify the square root of 24, see if we can get anything to come out. Let's see what it looks like. So tell me how to factor 24. What's going to go into it that's prime? 2 goes 12, and then 2 goes 6, and then 2 goes 3. Now, because it's a square root sign, I can only take pairs, so that means one of those 2's got left over. And this is the first time we've seen one that looks like this. So what's going to come outside the radical on top? 2, because I have one pair I circled up. I take one from that pair, bring it outside. What goes underneath the square root sign? 3 times the 2 that's not circled. Whatever's not circled, multiply those back together. So that's what number? 6. Oh my goodness. I have 2 square root of 6 over 2 square root of 6. What does that equal? Because any number divided by itself equals 1, right? Because those cancel and those cancel, everything reduces down to 1 over 1. Makes sense? Look at 14. Any idea there what we might be able to do? This one looks kind of funny, doesn't it? Because most of the numbers, I mean, are already outside. What's under the radical on top is square root of 2, and then in the denominator it's square root of 5. And those don't factor anymore, do they? Okay, so what we're going to need to do with that is going to be what we're going to talk about down here. It's called rationalizing the denominator. And so let's just hold off on that for now. We looked at it. Right now, we don't have anything we see we can do to clean this thing up, so we're just going to leave it alone for now. And then talk to me about this one. What do you notice we could do? Okay, when you say simplify, simplify which part? In the top, square root of 16 is what? 4. So really, my numerator is 3 times 4, which is 12, over 36 times the square root of 3. Now, at this point, we are back to the problem of we've got a square root in the denominator, and we haven't yet learned how to get rid of it. So it's time to start talking about rationalizing the denominator, because we really don't want to leave it in this form. We're going to see how to get rid of a square root that's in the denominator here in just a second. So see if you can figure out what goes in the blanks on these. What rule do you think states that if I'm multiplying 2 square roots together, I could write them under one radical? That's the product rule. We've been using it. And then this is what we're going to learn about. The process of rationalizing the denominator. Oops, that's not supposed to have a cross on it. Sorry. Rationalizing the denominator is changing the denominator of a fraction from a radical to an expression that doesn't have a radical in it. And this, we've also been using, is going to be what rule? Quotient, because it's telling me if I have fractions, I can either have my radical over the whole fraction, or if I want to take the square root of the top over the square root of the bottom, that's legal too. And we can go either direction on that. So here's what we're going to do when we start rationalizing denominators. This is kind of like what we had on the answer up above. Okay. In fact, I want to go back up here for just a second so we can talk about this. If I look at this fraction, I don't have any radical on top. That's just the number 12. On the bottom, I have the number 36 times the square root of 3. As long as these numbers are both outside the radical, if they reduce down, I can do that. Can I reduce 12 over 36 to what? What goes into both of those evenly? 3 will. 3 goes into 12. Let me change my color here for a second. Okay. So 3 goes into 12, 4 times 3 goes into 36. How many times? 12 times. Hey, that's going to reduce more because now I've got a 4 on top, 12 on bottom. What goes into both of those? 4. 4 goes into 4 one time. 4 goes into 12 3 times. So here's what I have. A 1 on top over 3 times the square root of 3 on bottom. Now, the issue is I got to make sure that I never try to reduce something that's under a radical with something that's not. They are not the same animal. 3 is not the same thing as the square root of 3. They're completely different numbers. So if I have something under a radical and it's not a perfect square and I've already simplified that radical as much as I can, this guy cannot be reduced down or crossed out with anything that's not under a radical. But I can make the radical go away from the denominator if I rationalize it. Here's how it works. If I take this 1 over 3 times the square root of 3, I have no problem with this 3 being in the denominator. I just want to get rid of the square root of 3. My things that are legal to do to be able to get a number in a different form is I can multiply by what you might call a clever form of 1. As long as I multiply the numerator and the denominator by the same thing, that's legal, right? It doesn't change the meaning of it. It just changes how it looks. So what can I multiply times the square root of 3 to make the square root go away? Another square root of 3. So if I multiply, I'm going to change colors again. Top and, oops, where do you go? Top and bottom by the square root of 3. That's going to make this go away. Because how much is the square root of 3 times the square root of 3? It's just 3. So these two multiplied together just turns into the number 3. And now, when that gets cleaned up, 1 times the square root of 3 is the square root of 3 on top, over 3 times 3 is 9 on bottom. That would have been the simplified radical form after we rationalized the denominator on number 15. Okay, it's a little tedious, but we can do this. So now, if we look back at number 1, we've got a -3 on top, a square root of 3 on bottom. I don't want to leave a square root on the bottom. So how are we going to clean that thing up? What can we do? I could multiply by a square root of 3. And if I multiply the bottom by a square root of 3, I got to do what? Also the top. Okay, so if I multiply straight across, what's my new numerator? -3 times the square root of 3. Now what's going to be in the denominator? Just 3. Because if I'm multiplying the square root times itself, it makes the square root go away. Now, am I done? Or can I do anything else? I got -3 square root of 3 divided by 3. What's outside? Say it again. It's just going to be a negative square root of 3. Because remember, whatever's outside the radical, if there are common factors, I can reduce those down. So if I go back to the fact that 3 goes into 3 one time, 3 goes into 3 one time, this is just a negative square root of 3. Final answer. It actually went from being a fraction to not being a fraction when I rationalized the denominator. And that's a simpler way of writing it. Okay, so let's look at number 2. What would we maybe want to do there? What's my problem? The denominator. I don't want a square root in it. And right now it's got the square root of 10. And that's not a perfect square. So what can we do? Multiply by top and bottom, right? So what's my new numerator? 15 times the square root of 10. What's my denominator? 10. Am I done? No, because what can I do? I can reduce down. What reduces? The 15 with the 10. Now, can I touch that 10? You better not. If it's under a radical, remember, it's hands off. I can't reduce something outside a radical with something that's under a radical. That's square root of 10, and he's just there. But 5 goes into 15 3 times, and 5 goes into 10 2 times. So this cleans up to be 3 square roots of 10 over 2. Simplified answer. Okay, give me a quick signal. How are we doing? Okay, we're somewhere on this scale. I see a lot of these, but I see some of these too. All right, talk to me about number 3. What do you want to do there? We can multiply bottom and top by square root of 8, can't we? Yeah, is there anything else we could do? Actually, there is, and it's an option. I could simplify the square root of 8 because if I do the prime factorization on 8, what do you multiply together to get 8 using prime numbers? You figured that out yet? 2 times 2 times 2. That's an option. Don't have to do it that way. So let's just multiply top and bottom by the square root of 8, because that's probably going to be the first thing you're going to think about. Okay, now, tell me what you're going to get. Which is? How much is square root of 3 times square root of 8? Square root of 24. Over, now what's going to be the denominator? That's the reason we did it, so we could get rid of the radical. Now, before you stop, here's where you'll have to be careful. You need to see if the square root of 24 can simplify. So if you didn't simplify the square root of 8 before you multiplied through, then you're going to have to check this numerator because it's probably going to simplify. So if you do prime factorization on 24, what goes into 24 that's prime? 2. How many times? 12. 2 goes into 12, 6, and 2 goes into 6, 3. So what can I circle up? Pair of 2's. And I'm going to multiply the 2 and the 3. So tell me what this is going to look like. What comes outside? Hang on. Look careful. The 2 comes to, remember what I circled up. So the 2 comes to the outside. And then I'm going to have the square root of 6 over this 8. Anything else, or are we done now? Perfect. Because that 2 over 8 reduces down. And it becomes the square root of 6 over 4. You guys are doing very, very well with this. Okay. Now, that's if we didn't simplify the square root of 8 before we rationalized. Look at number 4. What's our problem here? There is a negative on top. That doesn't worry me too much because it's not under a radical. Where's my radical? In the bottom. That's what I don't want. Now, do you think we might be able to simplify the square root of 12? Yes. In fact, I'm going to recommend this time, let's see what happens if we simplify before we rationalize. So we can kind of tell the difference. Is it going to be more steps or not as many steps? So right here is the factorization. I'm going to go to a different color so you guys can see it. Right here is the factorization for 12. So if I'm looking at that, I do have a pair of something. I've got a pair of what? 2's. So if I were to factor that 12 and then simplify the radical, what comes outside? 2. What stays underneath? The square root of 3 is going to be the radical part. Now, remember, numbers in the denominator are not a problem. It's the radical that is. And actually, is there a little more cleanup I could do at this point? What else can I do? I can reduce the 2 and the 4 because 2 goes into both of those evenly, right? So if I reduce this down, I now have a negative 2 over the square root of 3. And what would I do now to rationalize? Multiply times square root of 3, top and bottom, right? And what will I get on top? Negative 2 square roots of 3 over, and am I done? Yeah, nothing else reduces. You can't touch this 3 because he's under the radical. So it doesn't, you can't reduce it down with the 3 that's on the bottom. So it was a little bit faster if I simplify the radical before I rationalize, but it's okay to go either way, okay? When we're working with fractions, let me just kind of point out a couple of things here. So this one might bother you just a little bit because this is the square root of a fraction times the square root of a whole number. Is there anything I might want to change about that before I multiply? Okay, if I could think of the square root of 7 as the square root of 7 over 1, right? And I could put that whole thing underneath the radical because the square root of 1 is 1. So I could make that the square root of 5 over 21 times the square root of 7 over 1. Now, are these perfect squares? 5, 21, 7, 1. Those are not perfect squares. So I'm going to make this suggestion. What if, instead of leaving it as a square root times a square root, let's put it all under one radical, and we'll have the first number times the second. We said that was legal, right? We can either take a fraction and separate it out into the square root of the top over the square root of the bottom, or we could put it all together under one radical. And that's what I'm going to do. And what benefit do you think there might be if I write it this way? You think that? Say again. I could multiply straight across because that's how we multiply fractions. What else could we do before we multiply those? Do you see a common factor between top and bottom? The 7 and the 21. If I were to reduce this down, then this would equal the square root of 5/3, which I could think of as the square root of 5 over the square root of 3. Correct? Is that going to be hard to rationalize now? Because all I have to do is what? Multiply by square root of 3, top and bottom. And what will that equal? My numerator is square root of 15 over the whole number 3. Okay, so check to see if you can kind of clean up those fractions before you worry about having to deal with the radicals. I would do that. Do you notice anything we might want to do on 8? If I do the same thing here, put it under one radical, and I've got 3 over 2 times 5 over 6. You said we can reduce the 3 and the 6, right? 3 goes in there once, 3 goes into 6 twice, and now it looks like the square root of 5 on top over the square root of 4 on bottom. Oh, wait, what do you notice about that? What is the square root of 4? It's a perfect square. I don't even have to rationalize on this one. This is just going to turn into what? Square root of 5 over the whole number 2. Okay, we've been wading through kind of, I don't want to say deep stuff, but there's a lot of thinking that goes on with this, okay? And there's a lot of different routes you can go to get to the answer. And it's just kind of a matter of practice for you to get to a point where you feel pretty confident that you know what you're doing. Now, we already talked about what is any number raised to the 0 power. What does that equal? It's what? Any number to the 0 power equals 1. 1. And remember, we talked about that because if you were to look at another way of thinking about something raised to the 0 power, it would be the same thing as like x to the 3rd over x to the 3rd, which we know our exponent rules tell us we would subtract the exponents, but we also know what's any number divided by itself. It's 1. So that's why any number to the 0 power will always equal 1. Now, be real careful here. We've talked about this, but I want to kind of hammer this in because this is where you get in trouble with the calculator if you're not careful. In this example right here, what is my base? Remember, a base is what has the exponent on it. So what has the exponent on it? On this one? What is that? First of all, the exponent is what number? 3. What is being raised to the 3rd power? Just x. Remember, that exponent is attached to what's right in front of it, and what's right in front of it is just the x, and then that's going to get multiplied by the -2. But the next one, that exponent of 3 is attached to what? The negative 2x, because it's attached to the parentheses, and everything in the parentheses is the negative 2x. So you got to be very careful. You pay attention. If you had this, but you typed it in the calculator this way, you won't get the right answer, okay? Because the calculator is only going to think that you're cubing the x, because that's what order of operations would say. Now, let's double check and make sure we know how to do these. What is going to be the simplified answer if I have negative 3 in parentheses squared? Okay, I'm hearing positive 9 and I'm hearing negative 9. Can't be both. We got to figure out which one's right. Because what's getting squared? The number in the parentheses, which is negative 3. And negative 3 times negative 3 is positive 9. Now look at this guy. What's the simplified answer for that one? Is it going to be positive 9 or is it going to be negative 9? What's getting squared? It's just the 3, because the negative sign is not in a parentheses with the 3. So the only thing getting squared is the 3. And then after you square it, you multiply it by this negative 1 that's in front. Because this is really like negative 1 times 3 to the second power. Those are different answers. And your calculator is going to use order of operations according to how you type it in. So if negative 3 is what needs to get squared, you need to put it in the parentheses, okay? Now, what do you think a fraction raised to a power is going to be? 1/5 raised to the 3rd power means what? Means multiply it times itself 3 times. So that's 1/5 times 1/5 times 1/5, which would equal what? 1 times 1 times 1 is 1 over 125. Remember, we're multiplying. 5 times 5 times 5 is 125. What's getting raised to the 3rd power over here? Only the 1. There wasn't a parenthesis, so it's just attached to the 1. So what's 1 times 1 times 1? But the denominator stays 5. It didn't have an exponent on it. Okay, does that make sense? All right, now let's talk a little bit about negative exponents. We touched on it last class because we talked about, or I guess it was class, no, it was last class, I think, about what happened. What does a negative exponent mean? Does it tell you about the sign of the answer? It tells you about location. Now let's see why. I want us to fill this in. What would 2 to the 4th power be? It's 2 times 2 times 2 times 2, which is what number? 16. Okay, Patrick, you're right. Then 2 to the 3rd is going to be what number? 2 times 2 times 2 is 8. What's 2 to the 2nd? 4. What's 2 to the 1st? 2. Now I want you to notice something. 2 to the 4th was 16. What do we do to 16 to get to 8? Divide by 2. To get from 8 to 4, you divide by 2. From 4 to 2, you divide by 2. Does it make sense that our pattern here is we divide by 2 to get to 1 smaller on the exponent? What would 2 to the 0 be? 1, because 2 divided by 2 is 1. Now, what would 2 to the negative 1 be? Because we're going to take this number and divide by 2. 1 over 2, 1/2. Huh? Remember, that's our pattern. Every time we reduce the power by 1, we take the number above it and divide by 2. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. 1 divided by 2 is 1/2. What do you think 2 to the negative 2 power is? It's going to be 1 over 4. Now, the other thing we talked about when we said negative exponents was we said, remember, you can think of this as this, okay? If it doesn't look like a fraction, make it look like a fraction by putting it over 1. And then that negative tells us we do what with the base? Flip it. And after you flip it, then your exponent becomes positive. And what is 1/2 times 1/2? 1/4. So that's the other way you can think of it. We can see the pattern if we fill it in this way, but you got to remember when I see a negative exponent, it tells me nothing about the sign of the answer. It's telling me about location. Okay, so it's going to turn, if it started off as a whole number here, it's going to turn into a fraction, because when I flip it, it's going to be a fraction. Okay, so let's go to these and let's see if we can get these things evaluated correctly. All right, what's 28 to the 0 power? 1. What's negative 16 in parentheses to the 0 power? 1. What is a negative 7 raised to the 0 power?
-1.
Let's decide, is it 1 or is it -1? Take a vote for me. How many of you say it is +1? How many of you say it is -1? Okay, we are not completely in agreement. You tell me that 0 as an exponent is attached to which part? The 7 or the -7? The 7, then it's not in a parenthesis. So it means that 7 to the 0 power is 1, but there's a negative sign in front of it. That's -1. All right. Now, what is anything raised to the 0 power as long as that base is not 0? 1. What would 6y to the 0 power be? 6 times 1, which is 6. Ah, be careful. Without a parentheses, the only thing raised to the 0 power was the y. So y to the 0 becomes 1, and 1 times 6 is 6. Now, on F, what is that going to equal?
1.
Woo, I am hearing lots of different answers here. What's the 0 attached to?
6y.
The parentheses, which is 6y. So everything in parentheses to the 0 power equals 1. All right, you got it? Those can be sneaky. You got to pay close attention. All right, and we've covered this rule about when you multiply and bases are the same, what do you do with the exponents? You add them. So let's make sure we've got it down. 2 to the 4th times 2 to the 3rd would be what?
4, 6, 4.
Look at our rule. Yes, the base stays the same. 2 raised to the 7. Good, Kelsey. Okay, what would 6 to the 2nd times 6 to the 3rd be? 6 to the what power? I hear some 5s and I hear some 6s. Which is 5, because we add the exponents. Good job. Okay, now let's see if we can clean these up a little bit. I'm not too worried about the numbers. Let's make sure we know what to do with variables. What would x squared times another x be? X to the 3rd, because what's the exponent here, even though I don't see it? There's really a 1 there. And then when I add them, that's where the 3 came from. What would this one be? M to the, what do you think? Okay, I'm hearing 12. Y'all agree with that? Because what did we do with 4 and 3 and 5? Add them all together. M to the 12th. Good job. Okay, can I do anything with 2 to the 4th times 3 to the 5th? Not in terms of leaving it with an exponent, because look at my bases. Are they the same? No. So it's just going to stay that way. What about 2 to the 4th plus 2 to the 3rd? The only thing I could do on these is I could actually simplify to be, this would be 16 times, and 3 to the 5th is going to be, I think, 243, and I could multiply that out. That's kind of an ugly number. This one would be, the 2 to the 4th is 16 plus 2 to the 3rd is 8. But there's no way I can rewrite it as a base of 2 with an exponent. I have a rule for when I'm multiplying and bases are the same, and a rule for when I'm dividing when bases are the same, but not if I'm adding. And I don't have a rule if I'm multiplying and bases are different. So be careful that you watch out for that. But I'm wondering, can we do something with F? All right, what do you think this is going to turn out to be? Okay, because these are just numbers being multiplied together. 2 times 3 is 6. I agree with that. And then what is x to the 3rd times x to the 7th? X to the 10th. Make sure you keep your base, okay? Can I do anything with G? What can I do? Okay, so what does it look like when I add these? First of all, to add, do they have to be like terms?
Well, we do.
They do. And how do I know if they're like terms? They have to have the same base with the same exponent, and they do. So how do I add them? Remember? 13 what? X to the third. Very good. The variable and the exponent will stay the same. All I do is add up how many of them I have. Now, what about H? It's the same thing, except instead of adding, I'm multiplying. What would that be? 8 times 5 is 40. And then what do I write after that? X to the 6. Remember, if I'm multiplying and bases are the same, that's when I add the exponents. Lots of little rules here to remember. Okay, what about I? Negative 21. P to the 13th. Good job. Okay. And so we're almost done. We're going to review the power rule. And we've got 3 cases of it. So if I write this out using the definition of exponents, something raised to the 3rd power means I'm doing what? Multiplying it times itself 3 times. So that's the same thing as 2 to the 4th times 2 to the 4th times 2 to the 4th. Agreed? And I could actually break it down further, and I could do 2 times 2 times 2 times 2 for each one of these. But I also have a rule for when I'm multiplying and the bases are the same. I do what with the exponents? Add them. So what's 4 plus 4 plus 4? 12. And our shortcut is if I have an exponent and it's raised to another power, I do what with the exponents? How would I get from here to here? Multiplying, yeah. If I'm multiplying, I've got 2 different bases that are the same. That's when I add the exponents. But if I have one base with 2 exponents, that's when I multiply the exponents. So see if you can tell me what this would be. 5 to the 4th raised to the 5th power would be. Good, 5 to the 20th. What about this one? 8 to the 6th raised to the 3rd power. All right, so we've got that rule down, right? Okay, now look at this one. The difference here is we have a parentheses with an exponent on it, and there's more than one factor inside the parentheses. So what do I have to remember when I raise this to the 3rd power? What's getting raised to the 3rd power? Yeah, so that means 4x times 4x times 4x, which would equal what? What would 4x times 4x times 4x be? 4 times 4 is 16, and 16 times 4 is 64, x to the 3rd power. Does that make sense? Because x times x is the 3rd. And so here's our little shortcut. I'm going to take every different factor inside the parentheses and raise it to the 3rd power. This was 4 to the 3rd times x to the 3rd. Okay, let's see if you guys can tell me what 3xy in parentheses squared would be. What's the number part? 3 squared is 9. Good. Then what else?
X squared, y squared.
X squared, y squared. Because if we do it without parentheses at all, then we're going to write it that way. Okay, so that's 9x squared, y squared. Okay, see if you can tell me how to do this one. I've got negative 5m squared inside of parentheses raised to the 3rd power. So it's negative 5 times negative 5 times negative 5, which is a negative 125. Good. And then what else? M to the, which is it? Because I multiply the exponents. Good job. Okay. Can you figure out what to do on n? Okay, now you said distribute. Do I distribute before I take care of the exponents or after? Think PEMDAS. I'm going to have to distribute because that's multiplying after I take care of the exponents. So we're going to leave the 5 here, and then inside parentheses, tell me what you get when you do 2m squared m p to the third raised to the 4th power. Okay, so let's get the number part. What do you think the number part needs to be when we take all of this to the 4th power? Because it's 2 times 2 times 2 times 2, right? So 16 goes here. Then what? M to the, tell me again, 8th, and P to the 12th. And now, am I ready to distribute the 5? And that's going to give me what? 5 times 16 is 80. Well, now hang on a second. I use the word distribute, but am I really distributing? Because to distribute, I need more than one term. I'm not really distributing because there's no plus signs or minus signs. These are all factors. So I'm just multiplying the 5 times the 16, and then I'm keeping the m to the 8th, p to the 12th. If there were plus signs between all of those, then yes, each one would get a 5 multiplied in front of it. But I'm only just multiplying the numbers 5 times 16 to get this. Okay, does that make sense? All right, I know this is a lot of information, but I promise we're almost done. Okay, power rule is telling us that we want to be able to clean up when we have maybe more than one step that has to be taken care of. For instance, we may have a power rule, but then we also need to use the product rule, or we need to use the quotient rule. So let's make sure we don't get confused if these things get a little complicated. We've already done one like O. Could you tell me what P would look like if we get rid of parentheses? That would be what? That's pretty easy, right? I just have to make sure I raise each part of the fraction to the 10th power. There's nothing that's going to reduce down. Now, look at Q, because I've got something raised to the 3rd times something raised to the 4th. And I've got 2 different ways I could go on this. What do you think you want to do first? Okay, so you're saying let's take care of this exponent on the first parentheses, clean it up, and then do the exponent on the second parentheses and clean it up, and then I'll just multiply everything together. Okay, we can do that, right? Anybody see anything else we could do? Tell me what you mean by multiply first. Hang on a second. Let's go ahead and do what you were talking about. We're going to take 2m to the 3rd power. So that means 2m times 2m times 2m, which is going to be what? 2 times 2 times 2 is 8. M to the 3rd power times, now let's do 2m to the 4th power. So we had 2 times 2 times 2 is 8, times 2 more is 16, m to the 4th power. So if I multiply these together, what's 16 times 8? 48, 128, m to the 7th, because if I'm multiplying and bases are the same, that's when I add the exponents. Now, here's something you might have noticed. Is what's inside the parentheses the same? And if I'm multiplying when the bases are the same, what can I do with the exponents? Add them. This was the same thing as 2m to the what power? 7. Guess what 2 to the 7th power is? So that would have been another way you could get there, okay? Either way is fine, totally up to you. Talk to me about R. What could we do if this fraction is raised to the 2nd power?
the third times that 2. That 2 is the exponent, right?
The 2 is the exponent. So that's just telling me I'm multiplying this together 2 times. So one thing I could do is just write it out this way, right? Times another 5k to the third over 3. Is that permissible? Sure, you can do that. We'll do it this way. You guys tell me what you think this would be.
25.
So 25k to the 6th power on top over, what's on the bottom? 3 times 3 is 9. Okay, perfectly okay to do that. The other thing we could do is we could square each of these individual pieces. We could have thought of it as 5 squared. K to the third, when it's squared, becomes k to the 6th. And then 3 squared. And if you clean that up, you still get this. Okay, so you can go either way. Let's do t, and then I think we'll be good with this. So I've got -3xy squared to the 3rd power times x squared y to the 4th power. Now we saw a shortcut on this one. Would that shortcut work on t? Well, I'm saying, would there be a shortcut on that one? Are those like terms? They're not, are they? So if they're not like terms, then I can't do this with it. I'm going to have to clean up each one separately, right? Okay, so you guys tell me, if I cube this first parentheses, what would that be? What's -3 times -3 times -3? Because everything gets raised to the 3rd power. Positive or negative? Because there is a negative sign in there. That's a negative times a negative times a negative. So I've got a -27, x to the 3rd, y to the 6th. That's what happens when I clean up that first parentheses. What does the second parentheses become? X to the 8th, y to the 4th. Okay, now, do I have anything else I can clean up now that I've gotten this far? I've got some bases that are the same that are being multiplied together. So does anything happen to -27, or does it just stay the same? It stays the same. But I'm going to get x to the what power? I've got x to the 3rd here times x to the 8th here. If I put those together, that's how many x's? X to the 11th. Oops. What just happened? Now I'll pull it up. And then if I go to, stop that. If I go to the y's, tell me what you notice about the y's. There's how many of them? Y to the 10th. And that would be my simplified answer on that. Okay? So far, so good? Now, we could go through the same thing as far as the patterns on this to see what happens. But I want to see if you guys remember what happens when you have those negative exponents. Let's just see if you can tell me. It says solve by writing with positive exponents. So I've got 4 to the -3rd power. If I want to write it so the exponent is positive, what would that be raised to the +3 power? How do I get that exponent to be positive? What am I supposed to say again? When you say do the opposite, you mean flip it, right? But it doesn't look like a fraction. So what should I do? If I put it over 1, then when I flip it, it's going to turn into what? Excellent. 1/4 raised to the 3rd power. You can either put the whole thing in parentheses with the 3, or you could just put the 3 on the bottom with the 4. It doesn't matter because the 1 raised to any power is still 1. Okay, what would 6 to the negative 2 power turn into with a positive exponent? It'd be what? 1 over 6 to the second power. Good job. Okay, and then what if I start with a fraction and I have 1/4 and it's raised to the negative 2 power? So it would turn into 4 over 1, which is 4 to the positive 2 power. When I flip, yeah, which will be 16. When I flip the base, then the exponent becomes positive. All right, what about the fraction 2/3 raised to the negative 2 power? What would that become? Make it the fraction 3 over 2. And does it need parentheses? It does, because notice this whole fraction is being raised to the negative 2 power. I've got to show even after I flip it, the whole fraction is being raised to the positive 2 power. Okay, so keep in mind, negative exponents have nothing to, none of these are negative numbers. They're all positive numbers. It has nothing to do with the sign of the answer. It simply has to do with the location. So if we saw things like this, where we've got fractions and they've got negative exponents on it, like look at this one, x to the negative 3rd over y to the negative 2. Oh, sorry, yeah, I've kind of skipped a little bit, so I'm going to try to wrap this up here. What could that look like with positive exponents? So remember, so if I flip the location, I would have what on top? And what would be the exponent that goes with the y? The positive 2 over what's going to be in the denominator? X to the 3rd. Good job. All right. Now look at m. Some of them have negative exponents and some of them don't. This is where you got to be careful. So you tell me what needs to move. The h needs to move. Anything else? What else would move besides the h? The m. Do I need to move the 4? No, the 4 doesn't have a negative exponent on it. You leave it where it is. Do I need to move the k? No, it doesn't have a negative exponent. You need to leave it where it is. So I'm going to have a 4 on top. I'm going to have a k on bottom. Now I'll move these guys that need to move. So where does the h need to go? In front of the k with what kind of exponent? Positive 5. Anything going to go on top with a 4? M to the positive 2. Good job. Okay. So if we see bases that are the same, then you've got an option on how to clean this up. You're going to keep the same base, and your exponent is what you get when you subtract the 2 exponents that are here. So what is 11 minus 8? It's 3. And where was the larger exponent, on top or bottom? On the top. So this becomes 4 to the positive 3 on top. If I always subtract the smaller from the larger, it'll give me a positive exponent, and I just have to write it wherever the bigger exponent was. So look at P. My base is 3. I have an exponent of 7 on the top, 10 on the bottom. When I subtract those exponents, what am I going to get? Depends on which way I subtract. If I do top minus bottom, I get 3 to the negative 3 power, which means the same thing as what? Let's say I don't want a negative exponent. So if I think of it as 3 over 1 and I flip it, that's the same thing as 1 over 3 to the 3rd power. And I can either just put that exponent of 3 on the bottom, or I can put the whole fraction in parentheses with the exponent. But here's the other thing you could do. If you always subtract the smaller from the larger, 10 minus 7 is 3. But where was the bigger exponent, on top or bottom? On the bottom. And if it's on the bottom, I could put 3 to the 3rd on bottom, and that means there'd just be a 1 on the top. So you can go either way. If it's asking you for positive exponents, just subtract the smaller number from the larger on your exponents and write it wherever the larger one was. If you always want to do top minus bottom, just remember you may have to turn it into a positive exponent at the end. Would we have any concerns about any of the rest of this? Are we okay? I know as we get to things, if we need to do more on it, I figure we'll cover it. This is the last thing I want to show you. If you have polynomials and they're divided by a monomial, all right, we can clean these up if we do this. Remember, for it to be put together with one fraction, it had to have a common denominator at some point, and then you could put all the numerator together and put it over the one fraction. So we can go the opposite direction with this. We can take each term in the numerator, which, by the way, how many terms are in this numerator? 3, good, because they're always separated by what? Plus signs or minus signs. And I can take each term over this denominator and separate it out into individual fractions. Now, you may be wondering, why would I want to do that? Well, the reason is it makes it a lot easier to clean this guy up if I'm just looking at it as a single fraction. Because now, what could I do if I have 12 on the top, 6 on the bottom? Will that reduce down? Can I reduce those numbers? 12 over 6 is, could reduce down to 6 over 3, goes even further, it becomes what? Because you said if I divide 2 into each of these, that's 6 over 3, and then that reduces down to, well, 3 goes into 6 how many times? 2 times, goes into 3 1 time. So I just have the number 2 over 1 when I reduce down the number part. What can I do with m to the 6th over m to the 2nd? Subtract the exponents. What would that give me? M to the 4th. Should that be on the top or the bottom? On the top. I had more of these m's on top than the bottom. So that first term just cleans up to be 2m to the 4th. Plus, can you reduce this guy down? What do you do with 18 over 6? 6 goes into 18. Say it again. It's how many times? 3. 6 times 3 is 18. So I'm going to get a 3 on the number part. What about m to the 5th over m to the 2nd? Subtract and I get m to the, and does it belong on top or bottom? On the top, m to the 3rd. Plus, now what's going to happen here? 30 on top, 6 on bottom. 6 will go into 30 how many times? 5 times. So I get plus of 5, and then m to the 4th divided by m squared is m squared. That is your simplified answer for that. And it looked like it was going to be a big mess, I thought, at first. But if you break it into separate fractions, a lot of times you find it cleans up pretty easily. Now, I do want to show you F, and then we're going to call it done. And on F, I have how many terms in the numerator? I think I have 4. And each one of them needs to get divided by y squared. So what's going to be my first term? Y to the 6, and I'll divide that by y squared. Okay, then I'm going to put my plus sign, because that's the next sign I see. And then what goes on top? 8y to the 7th over y squared. Then I'm going to put my minus sign. And then what goes on top? 11y over y squared. And then I have another minus sign. And what goes on top? 4 over y squared. Okay. So what can I do with this first term? When I clean it up, what does it become? Well, the negative 9 doesn't have anything to reduce with on the bottom. There's just a 1 on the bottom. So I still have a negative 9. And then what do I do with those y's? And it becomes y to the 4th. Good job. Okay, so we've taken care of the first one. Now, look at the second term. What's that going to clean up to be? So tell me what I need to write. Plus 8y to the 5th. And that's y to the 5th on top, because I had more y's on top than I did on bottom. Then I need to write what sign? The minus sign. Good. Now, what's a little different on this fraction? I have more y's on bottom than I do on top, right? So if I wanted to write this with positive exponents, I know I still have an 11 on the top, but what am I going to get when I clean up the y's? If I've got 1 y on top and 2 y's on bottom. If I write it with a negative exponent, it'd be y to the negative 1. If I wanted to make it a positive exponent, where would the y belong? Do you understand what I'm saying? Okay, so you said 1 minus 2 is a negative 1. Is everybody good with that?
Yes.
Okay, can I write it now where the y doesn't have a negative exponent? Y to the negative 1 is the same thing as what? I could think of it as y over 1, but then I'd do what with it? Flip it. Where does the y belong? I could put it on the bottom, couldn't I? Okay, so let me... Two minus 1 is 1, but I had more y's on bottom than I did on top, so I put y to the first on the bottom. That's how I would do it if I wanted to have a positive exponent. And look at this guy. Is there even anything to clean up? No, I'm just going to recopy it. Does that make sense? I think you had one of these at the end of that first review section of homework. Didn't you? Wasn't there one that had something about cleaning up the quotient? Like these?
Which one?
I was thinking it was at the end of that first review homework. And so, yeah, you had some trouble on that. Maybe this will make more sense now. But we have finished up the review for 1.3.